So today we are going to discuss these two ideas, and as I said that I wasn't feeling well at all, so I haven't prepared any file beforehand. So let's just write whatever today's lecture is right away over here. So we're going to discuss what are vectors, and then we will have a look at what is matrix multiplication. And again, we're going to define these things in the context of linear systems. So let's again start with an example, and let's have a fresh look, another look at linear systems. So I'm gonna again write an example system. So you have some equation, some system of equations. Three variables and three equations. It doesn't have to be any restriction. I'm just starting with this example. Now, if I look at this equation, on the right hand side, I have a list of numbers over here, which define my right hand side of these equations. So you have a list of numbers. And I'm gonna treat this list as one object. So if I do that, I should better give it a name. So I'm thinking of it as one object, and this list of numbers which are arranged in a column. So I just call it a column vector. So what is a column vector? I got this idea because every time I have a system of equations, on the right hand side, I have a list of numbers. I'm just collecting them and thinking of them as one arrangement, one object, and call it a column vector. So it's just nothing except a list of numbers arranged in a column. A list of numbers arranged in a column. And I will have very specific symbols for it. They are slightly different from the book because book denotes them by bold letters. I can make bold letters here. So I am denoting these column vectors with an arrow. And to save a stroke, I'll just make arrow with only one spike over here. So this, in our above example, the vector which I had was this one. But in general, you don't have any restriction on how many numbers they could be in this list. You can have as many as you want. So each one of these numbers which are arranged in the column, this would be called component of the vector. I'll sometime call it vector, but you should just take it as a shorthand for a column vector. And how many numbers you have, like over here you have n. This is called the dimensionality or dimension of the vector. So this is a 3-dimensional vector and this is an n-dimensional vector. Now why I want to introduce this notation? For again, just to have some ease in thinking, we are used to of thinking the simplest equations, algebraic equations, they have constant, some variable. So one equation and one variable. Let's say this is your equation. So on the right hand side, you have some known quantity, and on the left hand side, you have some unknown quantity x multiplied with again with something known. So to get x, you simply do this. So I'm gonna do the same idea, but since I have a system of equations, I won't have a number over here. I'll write it as one single big equation, but with a list of number on the right hand side. And on the left hand side, I have again a number of variables, number of unknowns. So I'll arrange them in a list again. So you can arrange the unknowns in a list or in a column vector. So like in our example, that would be there's some vector and the unknowns were x, y, z. So my problem, typical problem of solving the linear systems becomes finding the unknowns, the unknown components of these vectors. Components of a vector. And so I would like to write it, just I would like to give it a form like this. A form like this. So what I need to do is you have these unknowns, unknown vector, which is equal to some known vector. This known vector has the constants, and this unknown vector is the unknown variables. And then I multiply it with something so that I generate my equations over here. So I know what I need to have here. I have, if I look at these guys, these two vectors, I have a vector on this side. I can think of the left hand side as also one number, which is equal to 3, but written in terms of the unknowns. So I can think of this as vector. And this is the first component of it. And this component should match with this component if the two vectors are equal. So maybe I should write it over here. Two vectors are equal if they corresponding, not random, if their corresponding components are equal. Components are equal. So that means I need to make this vector to get my equation. Now I want to split this open and write it as, so what I would see is that I have to write it as I was writing it as XYZ. X, Y, Z. This side was 3 minus 1, 4. And I'm just going to split it open. I'm going to write a matrix over here. And the only matrix I have at hand is the matrix of coefficients. 1, 2, 1, 3 minus 1, minus 3, 2, 3, 1. Yes.
The XYZ that you wrote in this matrix, it's not the same XYZ as the variables, right?
They are same. This XYZ are the variables which you are trying to solve for. You have arranged them into a vector. So now you're thinking of your linear system of equation as a vector being equal to another vector. But on the left hand side, the vector has some unknowns. And even that I have split it open into this form over here. But I know, so now I have split it open, I have just defined it. So this is just definition or done by hand. But this will make sense if I define somehow a product. There's a product going on. This matrix A is acting on this column vector X. If it gives me back my required equations, then that will establish the rule. So this splitting open gives me a rule. Gives me a rule to define product. Sometimes people like to call it action, but let's stick with product of a matrix with a column vector. So the rule is whatever gives me back this thing. Let me just write it. So the rule is whatever is going to give me back my original equations. That's 3z, 3x minus y minus 3z, 2x plus 3y minus z is equal to 3 minus 1, 4. So I want this back, and this is nothing more than putting parentheses around your equations and replacing by 3 equalities by 1, because you just call them a list and you say that the two sides will be equal if each corresponding component is equal to the corresponding component on the other side. So all I'm saying is this is equal to this. What? Why is doing that? And this is equal to this. So these are just your original equations. You want them back. So when will this happen? What rule of this will give me this? So it's you can define it in two ways. Can see this happening in two ways. Or I should say you should think of it in two ways. So the one is that you take your matrix, now in this matrix you have itself, sorry, in this matrix, the matrix itself, excuse me, please, excuse me. In this matrix, you have 3 columns lying themselves. So you can think of it as having 3 vectors inside it. And on the other side, I had whatever I had. So I can think of that getting back those equations in 2 ways. One is that I look at these columns and then I make a linear combination of these columns. With the coefficients coming from the vector with which I'm multiplying this column. So what's a linear combination of vectors? If I am defining it this way, I should talk about what's a linear combination of vectors. By the way, just to give you an idea ahead, what I'm going to do is multiply this number which is sitting outside the vector into each component. Sorry. X, 3x, 2x, and then I sum the corresponding components. This sum tells me to do that. 2y minus y plus 3y plus z minus 3z plus z. So this gives me back my required equations. If I follow this rule, then I take each one of these components and multiply the columns with them. Now you can, to do that, I should tell you what's a linear combination. So this is one of the most important concept in linear algebra, linear combination of vectors. So if you have two vectors, V and W, let me give them some example values as well. So let's take 2, 3 and W as -1, 2. I can multiply each one of them by a number. So this is defined to be that you take the components and multiply each component with that number. And if I want to write, then, so this is multiplication of a vector with a number. Then I can add two vectors. So multiplication of a vector with a number gives me back another vector because I got a new list. So I got a column vector back. So I multiply V by a number, I get a vector. I multiply W by a number, I get another vector. And then I can add those two vectors as well. And when you add, you just add the corresponding components. So like for example, if I come for these two guys, if I make V plus 2W, it would be 2, 3 plus -2, 4. So I'll get a vector 0, 7. So this definition of linear combinations I have used over here. And what I have found is I must define, to get my equations back, that a matrix times a vector should be linear combinations of the column vectors inside the matrix. Of matrix with components of the vector. So that means I can write, because a matrix is a bunch of columns. You can think of it as a bunch of columns. So if it's a bunch of columns, I can write them as V1. I'm using V over there, so it was better call this X. V1, V2, and if the matrix has m rows and n columns, so obviously I'm going to have n column vectors arranged in it. So if you put n column vectors side by side, that gives you a matrix. And how many rows are in this matrix? How many rows? Hmm?
One, sir.
No, this matrix doesn't have one row because each column has a number of entries. Let's suppose each column has m entries. So
N
those
rows.
are the rows in your column or in your matrix. So the number of rows is equal to the dimension of these row vectors. Not row vectors, column vectors. Right? Because if there were m dimension of these or each of these columns, I can write those as 1, 1. The first label is the component label, and the second label is which vector I'm talking about. So mth component of the first vector. Over here, I have first component of the second vector, second component of the second vector, third component of the second vector, and then mth component of the second vector. So you keep going until you have your last nth vector. First component of the nth vector, second component of the nth vector. So you have a m by n matrix, which you can think of it as n column vectors, each of dimension m, lying side by side. Now, if I want to multiply it, this guy, with a vector, the formula I gave you was that you should make the linear combinations of each of the vector with each of the component of the column. So how many vectors I have in this? N vectors. And if I want to multiply it with a column vector over here, this guy, I better use all of the components in there. If I am not using some of them, that means I'm not talking about their relationship with each other. So if I have to use all of their components, so how many components I need in this guy? I have to make linear combination of n vectors and multiply with some numbers. So I need n numbers. So this vector better be n dimensional. So you can multiply an m by n matrix by an n dimensional vector, not otherwise. I picked up the wrong book. So let's take an example. So I have misplaced my notes. These are not the notes which I needed. So I'm just gonna make up everything over here right now. 3 minus 1. Yeah, well, let me change it. Yeah, that's fine. Minus 2, 1, 2, 1, 3. Two, 0, 1. Can I multiply these two guys? Why not?
Yes, sir, we can.
I can't?
We can.
So someone is saying you can. Why you can? They are saying you can't.
Sir, because you can multiply two vectors that have the same number of rows, I think.
There are no two vectors. There is one matrix and one vector. Well, I gave you the formula that take these column vectors. They are vectors inside the matrix. That's called the column vectors of the matrix. And make linear combination with the components over here. So I have three vectors and I have three numbers available. So I can make linear combinations. So what are those linear combinations? 2. This is the formula of linear combination which I wrote above. You need three numbers and you need to add the vectors. So what do you get? You get 2, 4, 2, 4 plus the 0 vector. 0 vector means all components 0 plus -1, 2, 1, 3. And then all I need to do is add these components. So 1, 6, 3, 7. And I'll get back a vector. When I multiply a matrix with a column vector, this is multiplication, I get back a column. But I multiplied with a three-dimensional column. I got back the four-dimensional column because I'll get back a combination of the vectors inside the matrix, which happen to be in this example four-dimensional. So I'll get that dimensionality back. So you multiply m by n with an n-dimensional vector, you get back an m-dimensional vector. And that is quite useful because अगर मैं यही लूँ example 1 3 minus 1 2 4 2 1 minus 2 1 2 1 3 and this time I do not multiply them with some specific numbers but by some unknown numbers. I know I'm multiplying a 4 by 3 matrix with a three-dimensional column, so I must get back a four-dimensional. So there would be something 3 2 minus 1 0. So what I will get is there will be over here I'll get a combination. So first one is x plus 3y minus z 2x plus 4y plus 2z. You don't need to compute this right now, I'm just doing it quickly. Plus z 2x plus y plus 3z is equal to, over here I get four numbers, which is what I wanted because I wanted to set up, if I think of this guy as a coefficient matrix, that means I am given four equations. 4 equations, but three unknown. That's quite okay. We have discussed these kind of systems. But to set up 4 equations on the right hand side, I need 4 numbers, and that's what I get. Yes. We will get the dimension of the vectors of the matrix. Because this matrix, I can think of any matrix as a bunch of column vectors lying side by side. And each one of them has dimensionality. Any question? Now this same example, let me copy this. So I take again the same matrix and multiply it with, can you guys stop talking? It just distracts me. Otherwise I have no problem. Well, let me go back to my original one because I'm deriving that I want something like this back from here. This is what I'm trying to derive. So let me come back to this example. So this matrix multiplication, this time I look at this matrix and I say, well, I can even think of these list of numbers. Let's use some other color. These list of numbers as some kind of vectors. I called things which are arranged in a column as vectors. So if I just flip it over, it's still a list. So let's call them row vectors. Not much difference from a row vector in a row vector and a column vector. You just flip over the column vector, you will get a row vector. But if I look at this guy, so now I can think of this matrix as not a bunch of column vectors lying side by side, but a bunch of row vectors sitting on top of each other. Right? Then I need to get this back. How can I get this back? I'm now in a sense multiplying each row with this column. So I take the first component of my column with the first component of the first row, second component of my column with the second component of the first row, I get this, and so on. I do this with each row. So this operation, let me write it over here. Multiplying a row vector with a column vector. कैसे हम कर रहे हैं? रो का पहला कंपोनेंट कॉलम के पहले कंपोनेंट के साथ, रो का सेकंड कंपोनेंट रो के सेकंड कंपोनेंट के साथ, and so on. So the definition of this guy is, yeah, the definition is that if you have a row vector now I'm going to adopt a notation for the row vector. So I'm just going to put a bar on it. If it has a spike, that's a column vector. If it doesn't have a spike, it's a row vector. The book makes it an arrow, but I'm just using this. So take this. I'm just writing a very general one because I'm writing a definition. And you have a column vector. Now to define this product of a row and a column vector, they both must have same dimensionality, same number of components. Then this product, invoke my notation. This product is just equal to product of the corresponding components. And this is called the scalar product. You are familiar with it. This is scalar product. Why a scalar product? Scalar means in this context that is just a number. Because when you multiply these two guys, what are you getting? You are adding a bunch of numbers. So in the end, you are left with a single number. No list, nothing, just a single number. So it's called a scalar product or a dot product. You can define it for two pure vectors as well. All you have to do that if you are given two vectors, convert one into row. And then you know the formula. And this is just the dot product. So in other words, if I ask you to make but strictly speaking, it's between a row vector and a column vector. This is just 2 into 1 plus 3 into 2 minus 1 into 3. So 2 plus 6 minus 1, 7.
Minus 3.
So now what you have discovered that to get this, we gave this formula, make linear combinations, but you can give an equivalent formula, which is take the dot product of the rows with your given column. So let's write over here. Matrix times a column vector. And by the way, I'm defining it in a particular order. That's the only order it works. You put the matrix on the left hand side and your column vector on the right hand side. It's just because your matrix is row 1, row 2. If it's an m by n matrix, how many rows it has? M. That's just the definition. So you have m row vectors, or I can give them another name. Let's call them, let's say, A1, A2, AN, M, sorry. So let me write it over here that if you have a matrix, you can very well write it like this. As a bunch of row vectors lying on top of each other. So a matrix with a column vector and this guy, let me write it more symbolically. So let's write it this way. A1, A2, AM. So this is a matrix and you're multiplying it with a vector B. So the formula says take this dot product. Make the dot product of each row vector with your given vector.
क्या करा रही है मिस?
Who's this? So just take the dot product of each row vector with your given vector. So how many row vectors you had? M. That means your answer would be an M component vector, because each dot product gives you one single number. So your end answer has M numbers arranged in a column, an M vector. But to make this dot product, each of this row vector must have a specific dimensionality. What should be its dimensionality? Because you are making a dot with V. कितनी? नहीं, M क्यों? Its dimensionality must match with the dimension of the V, because you can define the dot product only if the two vectors have same dimensionality. So dimension of row vectors in the matrix must be same as dimension of column matrix, column vector you are multiplying it with. Now that just means over here I have M row vectors of dimension, each dimension n. That just means I have a matrix of M by n dimension, and my vector is n dimensional, and that's what you found in the previous definition as well. So if I use this second method to compute this product, ये मैंने कहीं लिखा हुआ है, yeah.
डेट तो पूछो, आज क्या तारीख? लिखो तो क्या करा रही है मिस?
Can you please turn off your mic? Someone's mic is open and we are getting noise. So let's do that example again, but using this new way of thinking about it. किस कॉलम से हम कर रहे थे इसको? 201. Now I'm not thinking in terms of the column vectors of the matrix. I'm thinking in terms of these rows. These rows. And just making the dot products with this guy. With this guy over here. So what's the dot product of this row with this? The formula says 2 times 1 plus 3 times 0 minus 1 times 1. Then I take the second row and put it in the second place, writing the dot product. One, then 1 times 2 minus 1 times 0 plus 1 times 1, then 2 times 2 plus 1 times 0 plus 3 times 1, and I get 1, 5, 6, 2 plus 1, 3, and 2 plus 3, 5, which is the same as before. 1, 6, 3. There should be a 7 over here. 2, 0. Yeah, 2 times 2, 4. 4 plus 3, 7. So you get the same answer, thinking in both of these terms. Now, what I'm going to do, we have found how to define the product of a matrix with a vector. I'm going to generalize it. For now, you can say that you can ask me why are you making up this definition, but it seems like an obvious thing to do. I'm going to define a matrix multiplied with a matrix. So if I'm given a matrix over here, let's call it A, and another matrix over here, let's call it B, and I want to multiply them somehow. Just make up some definition. Well, what can I do? One option I have is from what we have seen so far. That I think of it as bunch of rows and think of this guy as a bunch of columns. So this matrix is of this form. Let's say A1, A2, AM, and this matrix, I'm writing it in this form, a column vector, V1, V2, Vn, some other number. So if I look at this matrix, these are a bunch of columns. So far I don't know how to multiply a matrix with a matrix, but I know what to do if I am just given one column, how to multiply it with a matrix. So I say, let's just do that. And what I'm going to get back, if I multiply this matrix with the first column of B, I know that I'm going to get a column, right? Because that's what we saw previously. You can multiply a matrix with the columns, and you can think of it in this term. Take the scalar product of first row with the first column. Scalar product of the second row with the first column. So let me even write it like over here. Row 1 dotted with column 1. row 2 dotted with column 1. Take all the rows and keep dotting them with the same first column of the other matrix. And that gives you a row that you put it in the matrix you are building up. By the way, to have this dot product, what should be the dimensionality? How the dimensionalities should match? Row 1, row 2, row 3, row m, all of their dimensionality should be same as the dimensionality of the columns. That means if the columns of B are p-dimensional, if each of these guys is p-dimensional, then the rows over here must also be p-dimensional. So this was arbitrary, but the middle dimension, so this p must match with the dimension of the vectors of the second matrix. But the dimension of the vectors of the second matrix is same as the number of rows in that, in B. So the number of columns in the first matrix must match the number of rows in the second matrix. So you build up your first column like that, then you take your second one and start dotting them. Row 1 with column 2, row 1, row 2 with column 2, so on to row m, column 2. Keep doing it for all the columns. There could be nothing more obvious to do. Take one column, dot it, because you know how to multiply one column with a matrix, put it as a new column. Take the second column, transform it, put it as a new column, and keep collecting them until you will have how many columns? Because you are doing it to each column of the B, as many columns as you had in the B. So m dot column n. So this would be your answer for the matrix, and what you have is the new matrix has m rows, same number of rows as the A, and n columns, because you are taking each row, so those rows remain same, but you dot them with each column which is there in the B, so you get n columns back. So this is your resultant. A multiplied with B, I shouldn't put a dot, A with B is this C, and that's how you construct it. Probably a good idea to take some example to So I have a 4×2 matrix, and I'm multiplying it with I don't want to do big numbers with this. So think of it as having these rows. Don't put any comma between them. These are just that's how you write the row vectors. Just separated by a space. So it has 4 rows. So 4 row vectors. That's your first matrix. And your second matrix has 3 columns. Let's call them W. Lying side by side. This is the bigger bracket for the matrix. And your resultant is just this product. पहले फर्स्ट कॉलम वेक्टर ले लें और सारी रोज को उससे डॉट कर दें. That should give you the first column. And so on. So what would be the answer? You know how to write, how to do the matrix multiplication, but it's very helpful when you think of it in terms of vectors, because we will be able to say, when we start thinking, we will start thinking geometrically about these vectors. You will be able to say a lot of things about matrices, which you won't be able to if you don't think in terms of these vectors. So इसकी इसके साथ dot ली है. The dot is very simple. 4 times 2, 8. 8 plus 1, 9. इसकी इसके साथ डॉट ली. 2 times 2, 4. 4 plus 3, 7. 1 times 2, 2 minus 1, 1. इसकी डॉट इसके साथ. 2 times 2, 4. 4 plus 1, 5. This is your first column. अब इसकी डॉट लेना शुरू करते हैं इन सब के साथ. 4 times 1, 4 minus 1, 3. 2 minus 3, minus 1. 1 plus 1, 2. 2 minus 1, 1. And then with the last one. So 12 plus 2, 14. 6 plus 6, 12. 3 minus 2, 1. 6 plus 2, 8. So you get a 3 by 3 back. Question? Question आपका? There's some confusion. You should just say there's no harm in saying. You have a question. Oh yes, sorry. You should say it. So that's one way of thinking about matrix multiplication. But I had another way of multiplying matrix with a bunch of columns. What was that? That was you think of this matrix as columns, not as rows, and then start making linear combinations with the given column. So you can do that again. So let's write it symbolically first. You have column, column, column. And in this one as well, you have columns. And our instruction was that take the components, start picking up components from, so we will again do column by column. Start picking up components from this column and keep making linear combinations of all of these. When you make a linear combination, you get one column back. So that would be your first column in your matrix. And then do with the second, you get the second column. So each column is a linear combination of columns of A, the first vector. Two components of columns of B. So I guess we can copy this example. And so I have this column. I have two columns over here. If I need to make linear combination through the columns of the second, I better have the same number of components in this, which is true over here. So all you do is 2 times, you take this one first and make linear combinations. Plus 1 times 1, 3, minus 1, 1. Now, this is you have got a column back, so this is the first column in your matrix. Then you pick this guy and make linear combination. 1 times 4, 2, 1, 2, plus 1 times 1, 3, minus 1, 1. And then pick this guy and get the another column. So you will get as many columns as you are making the linear combination. So you are doing 3, 4, 2, 1, 2, 1, 3, minus 1, 1. This guy is being multiplied by 2. So you can do that. It should be same, but let's just try to do it here and let's see if we get it. 4 times 2, 8, 8 plus 1 is a linear combination. A linear combination has components, but just matching the corresponding ones, adding them. Yeah, what?
सर -1 होगा ना ये सेकंड में जो आपने लिखा है मल्टीप्लाई करते वक्त सेकंड कॉलम से.
Second column, yeah, this is -1. Thanks for saving me. So 9, 4 plus 7, 4 times 2, 8, 8 plus 1, 9. And 2 minus 1, 1, 5. The second is 4 minus 1, 3, 2 minus 3, minus 1, 1 minus 1, 1 plus 1, 2, 2 minus 1, 1. And over here, 12 plus 2, 14, 6 plus 6, 12, 3 minus 2, 1, 6 plus 2, 8. So as I said, a matrix is a bunch of columns lying side by side, and that's what you get. In the end, if you want, you can erase these columns. And this is your matrix, and I hope this is the same as over here. Oh yeah. Yeah, it's same. So these are two ways. Well, we will discover two more ways, but these are the most important ones. Because you think in terms of two sets of vectors. Whenever you see a matrix, you should think of it as composed of either of two kinds of vectors, either column vectors or row vectors. Both are there. So let's stop at this point. I had to discuss a few things by now I've forgotten, except that is Friday okay for the tutorial or should we change it? Saturday is okay with everyone. Well, I have no way
What's
to.
the time?
Huh?
What's the time?
Just like last time, 5 p.m. I'll probably be switching. I'll just look at my convenience. Because everyone is giving me. Some people are saying Wednesday. पाँच बजे तो नहीं कोई क्लास होती. So any question from the other side? Yeah, I'll upload both. I was telling in the beginning of the class, I had some food poisoning. I couldn't do it. I wasn't feeling well at all. I'll do it right now. And I'll post the first homework today. Huh? Assignment, homework, yeah, whatever you want to call it. So as I said, that two people can join in a group. Well, you must join. You must find a partner. If you can't find one, huh? You will have a 1 week submit. Yeah, huh? I'll let you know. कैसे बताएं? All you have to do is write your partner's name. You have to submit one homework per group. Just write your partner's name.
सर सो दोनों पार्टनर्स में से किसी एक को सबमिट करना होगा ना?
दोनों में से कोई एक सबमिट करेगा. And if you can't get along with your partner, you are just failing at life, not only in this course.